The metric system began as a response to confusion. Before its arrival, many regions in Europe used their own local units, often based on body parts, harvest baskets, or city customs. A mile in one place did not always match a mile in another, and traders had to navigate a maze of conversions that changed from border to border. In the late 18th century, during a period of political and social change in France, there was a desire for something more regular and predictable. Reformers imagined a system built not on the habits of particular towns, but on features of the natural world that could be shared by everyone. The goal was to create measures that would be the same in every market, every laboratory, and every workshop. They discussed how length, mass, and time might be defined in a way that did not depend on kings, guilds, or local traditions. Out of this discussion came the idea of a coherent, decimal-based system, where larger and smaller sizes could be reached simply by shifting powers of 10. Over time, this cautious experiment would grow into a worldwide standard, but in the beginning, it was only an attempt to bring order to a scattered and inconsistent landscape. The early supporters thought that if they could align units with natural regularities, the measures would feel less arbitrary and more steady. Their vision was not dramatic, only patient and methodical, seeking calm, repeatable definitions that could be written down once and used quietly for generations. The first formal step in this direction was the creation of a new unit of length, the meter. French scientists proposed that it should correspond to a fraction of the distance from the equator to the North Pole along the meridian through Paris. Surveyors set out to measure this long arc of the Earth's surface using the best techniques they had at the time. The process took years and involved many corrections, adjustments, and recalculations as they tried to capture something vast with limited instruments. From these measurements, they defined a single length that would stand for everyday distances, for tools, and for scientific observations. This length was not tied to the arm of a king or the width of a grain, but to the shape of the planet itself, at least as they understood it. To give it a physical form, they created a metal bar that represented the meter, stored carefully so that other copies could be made from it. Around the same time, they introduced a new unit of mass called the kilogram, linked to the mass of a precise volume of water. This gave people a way to handle mass in a repeatable manner, using water as a reference rather than a local stone or a traditional weight. With these two core units, length and mass, they hoped to reduce old arguments about fairness and accuracy. The approach was straightforward and sober, based on the idea that a shared reference, once agreed upon, would reduce confusion for everyone using it. From the beginning, the designers of the metric system wanted it to be easy to scale. They chose prefixes to indicate powers of 10, such as kilo for 1,000, centi for 100th, and milli for 1,000th. With these prefixes, a person could move up and down sizes without learning entirely different unit names. A kilometer would simply be 1,000 meters, while a millimeter would be 1,000th of a meter, and so on. The same logic would apply to grams, liters, and other measures that would be introduced. This pattern made calculation more routine, especially when compared with older systems that relied on mixed bases and irregular fractions. For many users, the change was gradual and sometimes uncomfortable, but the underlying structure was meant to be stable. It allowed the same rules to govern a tiny measurement at the laboratory bench and a large one across a landscape. As the years passed, more fields began to adopt these units, recognizing that the shared pattern simplified teaching, bookkeeping, and technical work. Engineers, merchants, and scientists could speak to each other using the same combinations of prefixes and base units. This did not remove all errors or misunderstandings, but it did remove many sources of mismatch that had previously come from using unrelated units for similar tasks. The decimal arrangement made the system feel like a single connected framework rather than a patchwork of unrelated pieces. In the 19th century, interest in shared measurement standards moved beyond the borders of one country. International trade, scientific correspondence, and railroad construction all revealed the inconvenience of clashing measurement systems. Representatives from several nations met to discuss how they might coordinate their units, especially those linked to the metric framework that had already been outlined. These discussions led to the signing of a formal agreement known as the Meter Convention in 1875. The convention created an international structure to maintain and compare standard units for length and mass. A new international bureau was established to safeguard official prototypes of the meter and the kilogram, and to oversee comparisons with national copies. These prototypes took the form of carefully crafted platinum iridium artifacts, designed to be durable and stable over many years. Member states could receive their own copies, which would be regularly checked against the originals. This approach anchored everyday practice in a quiet chain of reference, stretching from precision laboratories down to workshops and markets. The system depended on patience, careful record-keeping, and cooperative measurement. It was not dramatic work, but it formed the basis for gradual alignment between different countries. With each comparison and each report, the shared units became more trusted, and users could become more confident that a meter or a kilogram meant roughly the same thing in different parts of the world. As technology progressed, new kinds of measurements became important, and the simple trio of meter, kilogram, and second needed to be extended. Electrical engineering called for units of current, voltage, and resistance. Thermodynamics required precise ways to talk about temperature and energy. Light measurements demanded clarity about brightness and frequency. To address these needs, international committees began to define a broader set of base and derived units, always trying to keep the structure coherent. Gradually, a system emerged that added units like the ampere for electric current, the Kelvin for thermodynamic temperature, the mole for amount of substance, and the candela for luminous intensity. These base units could then combine to form derived units, such as the Newton for force, the joule for energy, and the Pascal for pressure. Each definition was accompanied by detailed procedures for realization, comparison, and dissemination. Laboratories would develop methods to realize the unit at high accuracy, then link these realizations to working standards for industry and daily use. In this way, the expanded metric framework began to cover a wide range of physical quantities without abandoning its underlying decimal logic. The work of defining and refining units remained slow and deliberate, often taking many years between proposals, discussions, and formal adoption. The result was a network of units designed to work together without hidden gaps or inconsistencies. By the mid-20th century, the need for a unified and fully recognized international measurement system became more pressing. After years of partial agreements and evolving practice, the General Conference on Weights and Measures, which meets periodically to oversee these matters, decided to formalize a comprehensive system. In 1960, it adopted the International System of Units, often abbreviated as SI from its French name. The SI brought together the established base units, the coherent derived units, and the decimal prefixes into a single structured whole. It provided official symbols, consistent writing rules, and recommendations for use in science, engineering, and commerce. The intention was to offer a stable framework that any country could adopt, either by gradual transition or more direct policy changes. Over time, many nations incorporated SI into their legislation, educational materials, and technical standards. Some kept certain traditional units for everyday speech, while still using SI in formal documents and calculations. The spread of SI was steady rather than sudden, but its influence extended into many fields. Technical drawings, product specifications, and scientific reports increasingly relied on the same units, with the same meanings wherever they were produced. This reduced the risk of misinterpretation in international projects and made it easier to compare data from different sources. The SI served as a quiet background structure that allowed measurement to be shared with fewer complications. At the core of SI stand 7 base units. These are the meter for length, the kilogram for mass, the second for time, the ampere for electric current, the Kelvin for thermodynamic temperature, the mole for amount of substance, and the candela for luminous intensity. Each of these serves as a building block for describing various aspects of the physical world. The meter underlies measurements of distance, position, and wavelength. The kilogram supports descriptions of mass, inertia, and related mechanical quantities. The second is central to timekeeping, frequency, and periodic processes. The ampere relates to electric charge flow, the Kelvin to the thermal state of systems, the mole to counts of atoms and molecules, and the candela to the perceived brightness of light sources under defined conditions. Around these base units, many derived units are formed by simple combinations, such as meters per second for speed, watts for power, and coulombs for electric charge. The system includes consistent symbols such as m for meter, kg for kilogram, and s for second, which are used in equations, tables, and specifications. The intention is not to create complexity, but to give each quantity a clear place in a shared network. By relying on these 7 reference points, SI maintains coherence as new phenomena are studied and new technologies developed, since new units can be expressed in terms of these established bases. Although SI units are used widely, older units have not disappeared completely. In some regions, people still refer to inches, pounds, or gallons in everyday conversation, while technical documents quietly rely on meters, kilograms, and liters. Certain industries, such as aviation and maritime navigation, retain specific non-SI units by convention, while still relating them to SI for calculation and standardization. Over time, conversion factors have been carefully defined so that traditional units can be linked consistently to SI units. These factors are written with many digits, reflecting precise agreements rather than rough estimates. Engineers and planners often carry both sets of units in their work, gradually shifting toward SI as projects and regulations require it. Educational systems typically introduce SI as the main framework, even when older units linger in culture and commerce. This gentle coexistence can last for decades, but the steady presence of SI helps align new technologies and scientific practices across borders. As equipment, software, and technical standards evolve, they usually adopt SI as their common language, reducing the need for repeated conversions. In this way, the standardization process is less about sudden replacement and more about slow adjustment, where shared units provide a consistent reference for different habits and traditions. For many years, the kilogram remained the only SI base unit defined by a physical artifact, the international prototype kilogram stored near Paris. While practical, this arrangement carried certain limitations. The mass of the artifact could drift slightly over time compared with its copies, due to surface changes or contamination, even under careful handling. Metrologists, the specialists who study measurement, began to search for definitions that did not depend on unique physical objects. Instead, they aimed to relate units to stable properties or constants of nature that could be reproduced in laboratories across the world. In the late 20th and early 21st centuries, progress in quantum physics and precision instrumentation made this approach more realistic. Experiments showed how electrical measurements could be tied to fundamental constants with high reliability, and how atomic transitions could provide extremely stable time references. These developments encouraged a gradual shift away from artifact-based units and toward definitions grounded in invariant quantities. The process required many international comparisons, detailed uncertainty analyses, and patient discussions on wording and realization techniques. The goal was to keep everyday measurements unchanged at normal levels of accuracy, while quietly improving the long-term stability and clarity of the underlying definitions. In 2018, the General Conference on Weights and Measures approved a significant revision of the SI, which took effect in 2019. This revision redefined all 7 base units in terms of fixed numerical values of selected fundamental constants of nature. The speed of light in vacuum, the Planck constant, the elementary charge, the Boltzmann constant, the Avogadro constant, the luminous efficacy constant, and the hyperfine transition frequency of cesium-133 were assigned exact values. From these constants, the meter, kilogram, second, ampere, Kelvin, mole, and candela could be realized through appropriate experiments and apparatus. This approach means that no single artifact or location holds the ultimate reference. Instead, any suitably equipped laboratory, using agreed procedures, can realize the same units by tracing back to the same constants. In everyday practice, this change does not alter the reading on a household scale, or the size of a common ruler, because the new definitions were chosen to match the previous realizations as closely as possible. However, it does improve the scalability and resilience of the system, especially for high-precision work and future technologies. The link to constants allows the system to remain stable even as instruments and methods continue to evolve over many decades. Day to day, most people encounter SI units in simple and practical forms. Road signs may show distances in kilometers, while packaging lists mass in grams or kilograms and volume in milliliters or liters. Weather reports express temperature in degrees Celsius, a scale related directly to the Kelvin. Electricity bills refer to kilowatt hours, built from the watt, which itself combines the meter, kilogram, and second. Medical prescriptions specify milligrams of a substance per kilogram of body mass or per liter of solution. These examples illustrate how the same core units and prefixes can describe varied situations with a steady vocabulary. In industry, machine parts are often dimensioned in millimeters, tolerances are given in micrometers, and pressures in pascals or bar linked to SI. Laboratories record data in joules, coulombs, and moles, depending on the type of experiment. Over time, documentation practices, software interfaces, and instrument displays have been adjusted to show SI values by default. Even when alternative units are presented, they are normally tied back to SI through defined conversion factors. This quiet convergence helps reduce confusion, mislabeling, and costly errors, especially in complex projects that involve multiple organizations. The presence of SI in routine measurements supports a kind of unspoken coordination across many kinds of activity. Looking ahead, the metric system and the SI are expected to remain central to measurement, even as science and technology explore new domains. Emerging fields such as nanotechnology, climate science, and space exploration rely on clear, transferable units to compare results over long periods and large distances. New prefixes are occasionally introduced to handle extremely large or small quantities, extending the same decimal pattern that has guided the system from its early days. International bodies continue to meet at regular intervals to review definitions, consider new experimental evidence, and refine guidelines for use. The pace of change tends to be measured and cautious, with extensive discussion before any adjustment is made. Through this steady process, SI adapts without frequent disruption to users. This stability can be reassuring for those who design instruments, write standards, or plan infrastructure, since they can rely on units that do not shift from one year to the next. Behind the scenes, metrology institutes continue their work of calibration, comparison, and documentation, maintaining the links between primary realizations and everyday measurements. In this way, the SI remains both familiar in daily life and quietly refined at its highest levels. Thanks for joining us for this calm walk through the history and standardization of the metric system and SI units. If you're still awake, please stand by for our next program.